October 14th, 1943. Black Thursday. 291 B-17 flying fortresses crossed into German airspace. Destination Schweinfurt. Target the ball-bearing factories that kept Hitler's war machine running. What happened next became the single bloodiest day in American aviation history. German fighters hit them at 28,000 feet, wave after wave. Bf-109s diving from above. FW-190s slashing through formations. For 3 hours straight, American bomber crews fought and died in the thin, frozen air over Germany. Final count, 77 bombers destroyed or damaged beyond repair. 650 American airmen killed, captured, or missing. In one mission. And here's the detail that should make your blood boil. American P-51 Mustang pilots watched from 15,000 feet below. They could see the massacre happening above them. They could hear their countrymen screaming over the radio. But their engines couldn't climb high enough to help. The most beautiful fighter plane ever designed was useless at the altitudes where men were dying. But 3,000 miles away in Detroit, a 58-year-old automotive engineer had already solved this problem 11 months earlier. His name was Jesse G. Vincent. He built luxury cars for rich people. He had never touched an aircraft engine in his life. Yet this car mechanic was about to do something that Rolls-Royce called mathematically impossible. He would take 14,000 handcrafted British parts and turn them into American mass production. The result, 55 523 engines. 50,000 American lives saved. The complete transformation of World War II. This is that story. Rewind to September 1940. Britain was dying. The Luftwaffe had been bombing London for 3 straight weeks. RAF pilots were flying 4-5-6 sorties per day. Spitfires and Hurricanes were being shot down faster than factories could replace them. But the real crisis wasn't airframes. It was engines. The Rolls-Royce Merlin powered everything that kept Britain alive. Every Spitfire, every Hurricane, every Lancaster bomber. Without Merlins, the RAF would cease to exist within months. British factories were producing 200 engines per week. They needed 2,000. The mathematics of survival were brutal. At current production rates, Britain would run out of fighter engines by spring 1941. Hitler would achieve air superiority by summer. Invasion would follow by fall. Winston Churchill made a desperate decision. He sent a team to America with a simple request: help us build Merlins, or watch us die. The British delegation arrived in Detroit carrying wooden crates. Inside were 2 complete Merlin engines, hundreds of blueprints, and unwavering confidence in their methods. They approached Ford first. Henry Ford examined the blueprints, calculated the retooling costs, and declined. Too complicated, too expensive, too British. They approached General Motors. Same answer. Then someone suggested Packard Motor Car Company, a luxury automaker. No aircraft experience whatsoever. The British were skeptical, but desperate. Jesse Vincent met them in Packard's East Grand Boulevard headquarters. He was not an impressive physical presence. Average height, thinning hair, wire-rimmed glasses. He looked like someone's grandfather, not an engineering revolutionary. But when Vincent examined those Merlin blueprints, something shifted in his eyes. He saw the problem immediately. The Merlin was a masterpiece. 27 liters of supercharged fury producing 130 horsepower. A 2-stage, 2-speed supercharger that maintained full power at 30,000 feet. The finest aircraft engine in existence. It was also completely impossible to mass produce. Here's why. The Merlin contained 14,000 individual parts. Every single one was manufactured using the British standard Whitworth thread system. 55-degree thread angles. Radiused roots. Specifications dating back to 1841. American threads used 60-degree angles. Flat roots. Completely incompatible. A British bolt wouldn't fit an American nut. Period. But that wasn't the real problem. The real problem was philosophy. Rolls-Royce built engines the way Stradivarius built violins. Each one was essentially handcrafted. When a connecting rod didn't quite match a crankshaft, a skilled worker filed it until it fit. When bearing clearances varied, craftsmen adjusted them individually. This wasn't manufacturing. This was artistry. And artistry doesn't scale. Vincent turned to the British engineers and said something that shocked everyone in the room. "Your tolerances are too loose for us." Silence. The Rolls-Royce men thought they had misheard. Too loose. Their tolerances measured thousandths of an inch. Their supercharger clearances were tighter than human hair. They represented a century of precision engineering tradition. Vincent didn't blink. "You design for hand-fitting. We design for interchangeability. Any part must fit any engine. No filing, no adjusting, no craftsman making it work. That requires tolerances tighter than what you've specified." The chief British engineer leaned forward. "Mr. Vincent, with respect, that's impossible. The Merlin requires human judgment at every stage of assembly. You cannot reduce it to mechanical repetition." Vincent smiled. "Watch me." He signed the contract that afternoon. $130 million. The largest licensing agreement in automotive history. His board of directors thought he had lost his mind. What Vincent understood, and what Rolls-Royce couldn't grasp, was that precision and mass production weren't opposites. They were complementary, but only if you rebuilt the entire manufacturing philosophy from the ground up. Over the next 11 months, Vincent assembled a team of 1,500 engineers. Their task: translate 14,000 British parts into American production without changing a single dimension or losing a single horsepower. They started with the threads. Packard couldn't switch to American thread standards. That would make their engines incompatible with British aircraft and spare parts. A Packard Merlin had to be identical to a Rolls-Royce Merlin at the molecular level. So Vincent did something extraordinary. He purchased every Whitworth tap and die in North America. When that wasn't enough, he bought specialized threading equipment directly from Britain. When that wasn't enough, he built custom machines from scratch. His engineers trained American machinists in a thread system most had never seen. BSW for coarse threads. BSF for fine threads. BA for instrument fasteners. 3 separate British standards, each requiring different tooling. The result: Packard manufactured British threads to tighter tolerances than Rolls-Royce did. Perfect interchangeability. No hand-fitting required. Then came the bearings. Rolls-Royce used copper-lead alloy bearings that required careful break-in and frequent inspection. Good bearings, proven bearings, traditional bearings. Vincent's metallurgists had a different idea. They substituted silver-lead alloy with indium plating. Silver provided better load-carrying capacity. Indium created a microscopically smooth surface that reduced friction during break-in. When British engineers saw the specifications, they protested. This wasn't Rolls-Royce standard. This wasn't proven. This was American arrogance. Then they saw the test results. Packard bearings lasted 40% longer than Rolls-Royce bearings. They ran cooler under load. They required less break-in time. 6 months later, Rolls-Royce quietly adopted the American bearing design for their own engines. The supercharger was the heart of the Merlin's high-altitude performance. 2 impellers spinning at 30,000 RPM. Tolerances measured in 10,000ths of an inch. The slightest imbalance would destroy the engine instantly. Rolls-Royce balanced impellers by hand. Skilled workers added or removed microscopic amounts of material until each impeller spun perfectly smooth. It took hours per unit. Packard developed precision casting techniques that produced impellers so consistently accurate they required minimal balancing. They created dynamic test equipment that measured balance while impellers were actually spinning. Production time dropped from hours to minutes. Quality actually improved. August 2, 1941, 11 months after signing the contract. 2 Packard-built Merlins roared to life on test stands in Detroit. American engines. American workers. American methods. British specifications. They produced 130 horsepower each, exactly matching Rolls-Royce output. Vincent stood watching with his arms crossed. No celebration, no speeches, just a small nod of satisfaction. When Churchill heard the news, he reportedly wept. But building two engines that worked was meaningless. The real test was scale. Could Packard build 50,000 of them? Vincent transformed the East Grand Boulevard plant into something unprecedented. Dedicated machining centers for each operation. Statistical process control at every station. Tolerances verified continuously, not just at final inspection. If a crankshaft journal needed to measure 2.2495 inches, every crankshaft measured 2.2495 inches, not 2.2492, not 2.2498. Exactly right, every time. By late 1942, Packard was producing 400 engines per week, double Rolls-Royce's entire British output. By 1943, they were building engines faster than North American aviation could build Mustangs to put them in. The V1657 Packard's designation for the Merlin 66 produced 490 horsepower at 3,000 RPM. War emergency power pushed it to 1,720 horsepower. It maintained full performance at 40,000 feet altitudes, where the original Allison engine could barely function. When the first Merlin-powered P-51B reached England in December 1943, test pilots couldn't believe the numbers. Maximum speed 440 mph. Service ceiling 41,900 feet. Range with drop tanks 280 miles. For the first time in the war, American fighters could escort bombers all the way to Berlin and back. The Luftwaffe had no idea what was coming. German intelligence had monitored Packard's conversion with mild interest. An American car company building British engines, amusing, but hardly threatening. Everyone knew Americans couldn't match European precision manufacturing. That assumption was about to cost them the war. January 11, 1944. The first large-scale Merlin Mustang escort mission. 663 B-17s heading for aircraft factories deep inside Germany. For the first time, P-51Bs accompanied them all the way to the target. German fighter controllers vectored their interceptors to attack altitude. 30,000 feet. The standard tactic. Climb above the bombers, dive through the formation escape before American fighters could react. It had worked perfectly for 2 years. Today, silver shapes were waiting for them. Mustangs, at 32,000 feet. Above the German fighters. The Luftwaffe pilots had never seen American aircraft at that altitude. Their intelligence said it was impossible. The intelligence was wrong. What followed was a slaughter. German losses that day. 39 fighters destroyed. American bomber losses. 11. 2 months earlier, the same mission profile would have cost 60 bombers minimum. German pilots who survived reported something chilling. The American fighters were faster than them at altitude, higher than them, and there were hundreds of them. They called it der amerikanische Teufelsvogel, the American devil bird. Packard's Detroit factory was building their executioners. By March 1944, P-51D Mustangs with bubble canopies were arriving in theater by the hundreds, each one powered by a Packard V1650-7. Each engine containing 14,000 parts manufactured to tolerances tighter than Rolls-Royce ever achieved. Hermann Goering reportedly said, "When I saw Mustangs over Berlin, I knew the war was lost." He wasn't wrong. But the story doesn't end there. Because everything you've just heard, the threads, the bearings, the superchargers, the production miracles, all of it almost collapsed in the spring of 1944. A problem emerged that no one had anticipated. Not Vincent, not Rolls-Royce, not the Army Air Forces. The Merlin engines were failing, not occasionally, consistently, at the worst possible moment, in combat. And the cause was something so small, so insignificant, that engineers initially refused to believe it could matter. They were wrong. In Part 2, we'll uncover the hidden flaw that threatened to ground every Mustang in Europe. We'll watch American and British engineers race against time to find a solution. and we'll witness the moment when a simple mechanic from Kansas discovered something that PhD metallurgists had missed. The Merlin's darkest secret was about to surface. Jesse Vincent had done the impossible. 11 months. 6,000 new drawings. 14,000 parts translated from British craftsmanship to American mass production. Packard was building 400 Merlin engines per week, while Rolls-Royce struggled to produce 200. P-51 Mustangs powered by Detroit-built Merlins were escorting bombers all the way to Berlin. German pilots were dying by the dozens. The tide of the air war had turned. But in March 1944, something started going wrong. Engines began failing. Not on test stands, not during training flights. In combat. At the worst possible moment. 17 Mustangs lost in 2 weeks, not to enemy fire, to engine failure. Pilots reported the same terrifying sequence: full power, sudden vibration, sudden, catastrophic seizure. Then silence at 25,000 feet, with nothing but German-occupied territory below. The Army Air Forces grounded the entire P-51B fleet pending investigation. And Jesse Vincent was about to face the most dangerous enemy of his career. Not the Germans, not the Luftwaffe, his own military bureaucracy. March 18, 1944, Wright Field, Ohio. Vincent sat alone at one end of a long conference table. At the other end sat Colonel Marcus Henderson, Chief of Aircraft Engine Evaluation. Between them, 12 Army Air Forces officers who would decide the fate of the Merlin program. Henderson opened a folder thick with failure reports. Mr. Vincent, in the past 14 days, we have lost 17 aircraft to engine seizure, 11 pilots killed, 6 captured, all Packard V1650 engines, all manufactured at your Detroit facility. Vincent remained silent. Henderson continued. Rolls-Royce has been building Merlins for 8 years without this failure rate. You've been building them for 2 years. The conclusion seems obvious. A major at the far end of the table spoke up. Perhaps American automotive methods aren't suited for precision aircraft engines. Vincent's jaw tightened. With respect, Colonel, I'd like to see the failure analysis reports. Henderson slid a folder across the table. Bearing failure. Every single case. The main crankshaft bearings are seizing under combat load. Vincent opened the folder. His eyes scanned the metallurgical analysis. Then he saw it. A detail so small that Army engineers had dismissed it as irrelevant. Colonel, these failures all occurred in aircraft stationed at bases above the 52nd parallel. Henderson frowned. England. Yes, that's where we're fighting the war. And what's the average ambient temperature at those bases in March? I don't see how that's relevant. Humor me. Henderson turned to an aide who shuffled through papers. Average low temperature 28 degrees Fahrenheit. Average high 41 degrees. Vincent nodded slowly. The Merlin was designed for British conditions. Our bearing alloy performs optimally between 35 and 95 degrees Fahrenheit. Below that threshold, the indium plating contracts faster than the underlying silver-lead matrix. Under combat load, microscopic gaps form between the bearing surface and the crankshaft journal. The room was silent. At full power, those gaps allow oil film breakdown. Metal contacts metal. Seizure follows within 30 to 90 seconds. Henderson leaned back. You're telling me your improved bearings fail in cold weather. The bearings you claimed were superior to Rolls-Royce specifications. They are superior. Between 35 and 95 degrees, British specifications assumed Mediterranean deployment. North Africa, Italy. We're operating in conditions colder than either British or American engineers anticipated. Colonel Henderson closed his folder. Mr. Vincent, I don't care about metallurgical theory. I care about dead pilots. Until this problem is solved, the P-51B fleet remains grounded. And I'm recommending that we return to Rolls-Royce bearing specifications immediately. Vincent stood up. That would be a mistake. Excuse me. Rolls-Royce bearings have the same cold weather vulnerability. They've just been lucky. Give me 30 days. I can solve this. Henderson shook his head. You have 14. After that, we're returning to British specifications and reviewing whether Packard should continue manufacturing Merlins at all. Vincent walked out of that meeting knowing two things. First, he was right about the metallurgy. Second, being right wouldn't matter if he couldn't prove it in 14 days. But what he didn't know was that someone else had already identified the problem. Someone no one in that conference room would have considered worth consulting. Technical Sergeant William Bill Kowalski worked the engine maintenance line at RAF Duxford. Before the war, he had been a tractor mechanic in Salina, Kansas. No engineering degree, no metallurgical training. Just 20 years of keeping machines running in conditions that engineers never designed for. Kansas winters regularly dropped below zero. Kowalski had learned things about cold weather engine operation that no textbook taught. He had noticed something strange about the failed Merlins. Every engine that seized had been started cold and immediately run up to full power. Standard procedure. Get the aircraft airborne fast. But Kowalski remembered what happened when you did that to a John Deere tractor in January. The oil didn't flow right. The metal didn't expand evenly. Tolerances designed for normal operating temperature became death traps when everything was frozen. Kowalski had mentioned this to his commanding officer. The CO had dismissed it. These are precision aircraft engines, Sergeant, not farm equipment. But Kowalski kept thinking. On March 21st, 3 days after Vincent's meeting at Wright Field, a young lieutenant walked into Kowalski's maintenance hangar. He introduced himself as Robert Chen, engineering liaison from Wright Field. Sergeant Kowalski, I'm investigating the bearing failures. Your CO mentioned you had some unconventional ideas. Kowalski wiped his hands on a rag. Lieutenant, I've been working engines since before you were born. These Packard Merlins, they're beautiful machines. Best I've ever seen. But somebody designed them for California, not England. Go on. It's not the bearings. It's the warm-up procedure. We're running these engines cold. Oil viscosity is wrong. Thermal expansion hasn't happened. The bearings are taking load before they're ready. Chen pulled out a notebook. What would you suggest? 20-minute warm-up at 1,200 RPM before any high-power operation. Let the oil circulate. Let the metal reach operating temperature. Then and only then apply combat power. That's not standard procedure. Standard procedure is killing pilots, Lieutenant. Chen drove back to Wright Field that night. He found Vincent in the metallurgical lab at 2 a.m. running cold temperature bearing tests. Mr. Vincent, I think I found something. Vincent listened. Then he ran the numbers. Kowalski was right. At 28 degrees Fahrenheit, the oil viscosity in a cold Merlin was 340% higher than at operating temperature. The oil wasn't lubricating, it was strangling the bearings. A 20-minute warm-up would solve 90% of the failures. No bearing redesign required, no production changes, just a procedural modification. But Henderson would never accept a solution from a Kansas tractor mechanic. Not without proof. Vincent had 11 days left. April 1st, 1944. RAF Steeple Morden. Vincent had convinced Henderson to allow one final test. 3 P-51’s. 3 different warm-up procedures. Full combat simulation at 30,000 feet. Aircraft 1 would follow standard procedure. Cold start, immediate full power climb. Aircraft 2 would use a 10-minute warm-up at idle. Aircraft 3 would use Kowalski's 20-minute protocol. 1,200 RPM until oil temperature reached 40 degrees Celsius. The test pilots were volunteers. They knew the risks. Henderson stood on the flight line with his evaluation team. If all 3 engines failed, the Packard program was finished. Vincent's career was finished. American Merlin production would end. 0600 hours. Temperature 31 degrees Fahrenheit. Aircraft 1 started its engine. Immediate taxi. Full power takeoff. The Mustang clawed into the gray English sky. At 22,000 feet, the pilot reported fluctuating oil pressure. At 24,000 feet, the engine began vibrating. At 25,500 feet, catastrophic bearing seizure. The pilot bailed out over friendly territory. The aircraft was lost. Henderson turned to Vincent. One down. 06 on 12 hours. Aircraft 2 completed its 10-minute warm-up. Takeoff. Climb. The pilot reached 28,000 feet without incident. Then 30,000. Then 32,000. At 34,000 feet under full combat power simulation, the oil pressure began dropping. At 35,000 feet, the pilot reported rough running. At 36,000 feet, he wisely reduced power and descended. The engine survived, but barely. Post-flight inspection revealed bearing damage. Henderson made a note. Marginally better, not acceptable. 06:35 hours. Aircraft 3, Kowalski's protocol. The pilot ran the engine at 1,200 RPM for 20 minutes. Oil temperature climbed slowly. 20 degrees Celsius. 30, 35, 40. Then he advanced the throttle. The Mustang lifted off and began climbing. 25,000 feet. Normal. 30,000 feet. Normal. 35,000 feet. Normal. The pilot pushed the engine to war emergency power. 1,720 horsepower. The absolute maximum the V1650 could produce. 40,000 feet. Oil pressure stable. Engine temperature nominal. No vibration. He held full power for 15 minutes, then dove to simulate combat maneuvering, then climbed back to altitude, then repeated the cycle. 45 minutes of simulated combat at maximum performance. The engine never missed a beat. When the pilot landed, Vincent was waiting at the hardstand with Kowalski beside him. Henderson walked over slowly. His face was unreadable. "Mr. Vincent, 20-minute warm-up. That's your solution. Not a bearing redesign, not a metallurgical innovation. A warm-up procedure." Vincent nodded. The simplest solutions are often the best. Henderson was quiet for a long moment. Then he extended his hand. "Get it documented. Get it distributed. I want every P-51 unit in the ETO using this protocol within 72 hours. He paused. "And Mr. Vincent, next time you have a problem, maybe start with the men who actually work on the engines." Vincent glanced at Kowalski. Noted. Within 1 week, the new warm-up protocol reached every P-51 squadron in England. Bearing failures dropped by 94%. The grounded fleet returned to service. But implementing a solution at headquarters was different from implementing it in the field. Fighter squadrons operated on tight schedules. Every minute on the ground was a minute not escorting bombers. Many pilots resisted the new protocol. 20 minutes was an eternity when German fighters were mauling B-17s over the Reich. Vincent made a decision that surprised everyone. He flew to England himself. For 3 weeks he visited frontline squadrons. He explained the metallurgy in terms pilots could understand. He showed them the failure photos. He introduced them to Kowalski, who flew over as Vincent's technical advisor. A tractor mechanic from Kansas teaching fighter pilots about engine management. The absurdity wasn't lost on anyone. But Kowalski spoke their language. He understood what it meant to depend on machinery in hostile conditions. He explained the warm-up protocol not as a regulation, but as a survival technique. By May 1st, compliance was nearly universal, and the results spoke for themselves. April 1944, losses to engine failure, 23 aircraft. May 1944, losses to engine failure, 2 aircraft. June 1944, losses to engine failure, 1 aircraft. The Merlin was back, stronger than ever. But across the English Channel, German intelligence had been watching. They had intercepted communications about the grounding. They had monitored the test flights at Steeple Morden. They had noted the sudden surge in P-51 activity after May 1st. Luftwaffe engineers began examining captured Mustang engines with new intensity. They were looking for the weakness that had temporarily grounded the American fleet. They wanted to know if they could exploit it. And in Berlin, a decision was being made. If the Merlin-powered Mustang couldn't be stopped in the air, perhaps it could be stopped on the ground. German intelligence identified Packard's East Grand Boulevard plant as the single greatest threat to Luftwaffe air superiority. One factory, 55,000 engines, the heart of American fighter production. What if that factory simply disappeared? In Part 3, we'll uncover Operation Elster, the German plan to sabotage American aircraft production. We'll follow the FBI agents who discovered the plot just weeks before execution. And we'll witness the moment when Jesse Vincent realized that his greatest enemy wasn't metallurgy or bureaucracy. It was a team of German saboteurs already inside the United States. The war was coming to Detroit. Let me remind you where we are. Jesse Vincent, a 58-year-old automotive engineer, had done what Rolls-Royce called impossible. He translated 14,000 handcrafted British parts into American mass production. Packard was building 400 Merlin engines per week. Then disaster struck. Engines failed in combat. Pilots died. The entire P-51 fleet was grounded. A Kansas tractor mechanic named Bill Kowalski discovered the solution. Not a redesign, not new metallurgy. A 20-minute warm-up protocol that solved 94% of the failures. By May 1944, the Merlin Mustangs were back, stronger than ever, escorting bombers deep into Germany. But across the English Channel, the Luftwaffe had been watching, and they were terrified. In April 1944, German fighter losses exceeded 400 aircraft. In May, that number climbed to 530. In June, it reached 623. These weren't just machines. Each aircraft represented months of production. Each pilot represented years of training. Germany was losing both at a rate that couldn't be sustained. Reich Marshal Hermann Göring demanded answers. The reports from frontline commanders were unanimous. The American Mustangs were everywhere. They flew higher than German interceptors. They flew faster. They could stay in combat longer, and there were hundreds of them. German intelligence identified the source. A single factory in Detroit was producing more Merlin engines than all of Britain combined. Göring issued a direct order. Find a way to neutralize the Mustang threat, or find a way to destroy the factory producing its engines. German engineers worked desperately to counter the Merlin's high-altitude advantage. They modified the Bf-109K with improved superchargers. They accelerated development of the Me-262 jet fighter. They experimented with rocket-boosted interceptors. They even considered mounting heavy anti-aircraft guns on converted bombers to attack formations from below. Nothing worked. The 109K couldn't climb fast enough. The Me-262 had technical problems and fuel shortages. The rocket interceptors were suicide missions. The bomber-destroyers were shot down before they could fire. For every solution Germany attempted, the Mustangs had an answer. By July 1944, Luftwaffe fighter pilot life expectancy had dropped to just 17 combat missions. New pilots were being thrown into battle with barely 40 hours of flight training. Many died on their first engagement. German ace Adolf Galland later wrote, "The Mustang made the American daylight bombing offensive possible. Without it, we might have held. With it, we were slowly strangled." But the Luftwaffe wasn't giving up. If they couldn't win in the air, perhaps they could win on the ground. Operation Elster, the Magpie. German intelligence had identified 23 critical American industrial targets. At the top of the list, Packard Motor Car Company, Detroit. The plan was elegant. 2 German agents, both naturalized American citizens recruited before the war, would enter the United States via U-boat. They would carry forged documents, American currency, and detailed plans of the Packard facility. Their mission: infiltrate the factory, identify critical choke points in the production line, and sabotage them in ways that would appear to be industrial accidents. A fire in the supercharger machining section, contaminated bearing materials, precision tools quietly damaged. Nothing dramatic, nothing traceable. Just enough to cripple production for months. The agents landed on the coast of Maine on November 29, 1944. They never reached Detroit. FBI counterintelligence had been tracking Operation Elster for months. German codes had been broken. The landing site was known. The agents were arrested within hours of reaching shore. Vincent never learned how close he came to disaster until after the war. But the Luftwaffe's desperation revealed something important. The Merlin Mustang wasn't just winning battles. It was breaking the entire German air defense system. And nowhere was that more clear than in the skies over Berlin. March 6, 1945. The largest American air raid on Berlin in history. 329 B-17 and B-24 bombers. 733 fighter escorts. Primary target, the Daimler-Benz tank engine factory and the Bosch electrical works. The 8th Air Force had hit Berlin before. Every raid had been costly. German defenses around the capital were the heaviest in Europe. Flak batteries, interceptor squadrons, early warning networks. Attacking Berlin meant accepting losses. But March 6th would be different. The bomber stream crossed into German airspace at 0847 hours. Temperature at 28,000 feet, minus 40 degrees Celsius. The new warm-up protocols had been followed to the letter. Every Merlin was running perfectly. German radar detected the formation at 0903. Fighter controllers scrambled everything they had. The Americans counted them. 312 German interceptors rising to meet the formation. Bf-109Ks, FW-190s. Even a handful of Me-262 jets. It was the largest Luftwaffe defensive effort in 6 months. The German fighters climbed toward the bomber stream, expecting to engage at 30,000 feet as they always had. They expected the American escorts to be below them, unable to reach their altitude. They were wrong. P-51D Mustangs were waiting at 33,000 feet. Higher than the German aircraft could efficiently climb. Faster than they could effectively maneuver. And there were 489 of them. Major George Preddy, leading the 352nd Fighter Group, saw the German formation climbing below him. Tally-ho! Bandits at Angels 25, going down. The Mustangs dove. German formation discipline collapsed within seconds. Pilots who had expected to attack suddenly found themselves defending. FW-190s that had been climbing steadily were caught in vulnerable positions with low energy and poor angles. The first pass killed 14 German aircraft in 90 seconds. Captain William Wisner of the 352nd recorded 3 kills in his first diving attack. He pulled up, rolled, and dove again. 2 more kills. 5 German fighters destroyed in under 4 minutes. The German formation scattered. Some tried to flee east. Some dove for the deck. Some simply panicked. Lieutenant Urban Drew spotted a flight of 4 Me-262 jets attempting to climb to attack altitude. The jets were faster than his Mustang in level flight, but they were slower in the climb. Drew dove on them before they could accelerate. 2 Me-262s destroyed. The most advanced fighters Germany possessed, killed by an aircraft powered by an engine built on an American automotive assembly line. The bomber stream reached Berlin virtually unmolested. For 3 hours, American aircraft pounded the German capital. The Daimler-Benz factory lost 67% of its machine tools. The Bosch works suffered structural damage that would take months to repair. Secondary targets across the city were hit with precision that would have been impossible a year earlier. German fighters attempted to reform and attack. Every attempt was intercepted by Mustangs. The escorts were everywhere at every altitude in every direction. By 14:30 hours, the last American aircraft crossed back into friendly airspace. The numbers told the story. American aircraft lost to enemy action, 8 bombers, 3 fighters. German aircraft destroyed 119, confirmed 47 probable. That ratio was catastrophic for Germany. They had thrown everything they had at the largest raid of the war. They had lost 15 fighters for every American aircraft destroyed. German pilot casualties that day exceeded 90 killed or captured. Many of them were instructors pulled from training units, men who couldn't be replaced. General James Doolittle called it the day we broke their back. He wasn't exaggerating. After March 6th, the Luftwaffe never again attempted a large-scale interception of American daylight raids. They simply didn't have the pilots or the aircraft. The ones they had couldn't compete with Merlin-powered Mustangs. In April 1945, German fighter opposition effectively ceased. American bombers flew over the Reich almost unopposed. The air war was over. The statistics of 1944 and 1945 revealed the magnitude of what Packard had achieved. Before the Merlin Mustang, American bomber losses averaged 7 to 9% per mission. After, losses dropped to 1–2%. Before, Luftwaffe fighter strength exceeded 1,500 operational aircraft. After, fewer than 300 remained by April 1945. Before, German aircraft production was still increasing despite Allied bombing. After, production collapsed as factories were destroyed and supply chains severed. The 8th Air Force estimated that the Merlin Mustang saved approximately 50,000 American aircrew lives, not by protecting them in combat, but by destroying the enemy's ability to resist. Major General William Kepner, commander of the 8th Fighter Command, wrote, "The P-51 Mustang, powered by the Packard Merlin, was the weapon that made strategic bombing possible. Without it, we would have been forced to abandon daylight operations entirely." Jesse Vincent received the Army-Navy E Award for production excellence. His factory built 55 523 Merlin engines by the time production ended in September 1945, more than all British factories combined. Bill Kowalski returned to Kansas after the war. He received a letter of commendation from the Army Air Forces, but declined any public recognition. "I just fixed what was broken," he told his family. "That's what mechanics do." The German agents from Operation Elster were tried and convicted of espionage. They spent the rest of the war in federal prison. The factory they had been sent to destroy produced engines until the day Japan surrendered. Goering was captured in May 1945. During interrogation, he was asked about the turning point of the air war. "The P-51, he answered without hesitation. "When I saw those fighters over Berlin, I knew the jig was up." But statistics and testimonials don't capture the human reality of what happened. In air bases across England, young men who expected to die finished their tours and went home. Bomber crews who had watched friends explode in midair completed their missions and survived. Fighter pilots who had been outnumbered 5–1 suddenly found themselves with empty skies and no one to fight. The Merlin didn't just change the war. It changed thousands of individual fates. Sons came home to mothers. Husbands returned to wives. Fathers met children who had been born while they were overseas. All because a car company engineer figured out how to build a British engine faster and better than the British could. But the story doesn't end with victory. What happened to Jesse Vincent after the war? What happened to the revolutionary techniques Packard developed? What happened to the partnership between British innovation and American manufacturing? And what lessons does this forgotten chapter of history hold for the challenges we face today? In Part 4, we'll follow Vincent through the post-war years and discover how the Merlin project influenced everything from jet engines to modern automotive manufacturing. We'll learn why Packard, the company that saved Allied air power, no longer exists. And we'll understand why this story, one of the most important engineering achievements of the 20th century, has been almost completely forgotten. The war was over, but the legacy was just beginning. Let me take you through everything we've witnessed. A 58-year-old automotive engineer named Jesse Vincent accepted a challenge that Rolls-Royce called impossible. He translated 14,000 handcrafted British parts into American mass production without losing a single horsepower. When engines failed in combat, a Kansas tractor mechanic named Bill Kowalski discovered the solution that PhD engineers had missed. A simple warm-up protocol saved the entire program. By March 1945, Merlin-powered Mustangs dominated the skies over Germany. The Luftwaffe was broken. Strategic bombing succeeded. The air war ended not with German victory, but with German collapse. 523 engines, 50,000 American lives saved. The complete transformation of World War II. But what happened to the men who made it possible? And why has this story been almost completely erased from history? Because success sometimes comes with a price that nobody expects. September 2nd, 1945. VJ Day. Jesse Vincent stood in his Detroit office listening to radio reports of the Japanese surrender. He was 59 years old. His hair had gone completely white during the war years. His hands trembled slightly from exhaustion. He had received the Army-Navy E Award. His factory had been praised by generals and presidents. The engines he built had won the air war over Europe. But Vincent knew something that the celebrating crowds didn't. Packard Motor Car Company was dying. The war had consumed everything. The entire factory had been converted to military production. Civilian automobile manufacturing had ceased in 1942. When the war ended, Packard had no new car designs, no updated production lines, no way to compete with Ford and General Motors, who had maintained some civilian production throughout the conflict. Vincent had saved American air power. In doing so, he had inadvertently destroyed the company he loved. Packard attempted a post-war recovery. They introduced new luxury models in 1946 and 1947. But the market had changed. Americans wanted affordable family cars, not expensive luxury vehicles. The company that had once built automobiles for presidents and movie stars found itself selling fewer than 100,000 units per year. Vincent retired in 1949. He was 63 years old. He had spent 40 years building the finest automobiles in America, then 4 years building the finest aircraft engines in the world. Now he was an old man with nothing left to build. He died in 1962 at the age of 76. His obituary mentioned his automotive career. It barely mentioned the Merlin. Packard Motor Car Company ceased independent operations in 1956. The brand that had helped win World War II was absorbed by Studebaker, then disappeared entirely by 1958. Bill Kowalski returned to Salina, Kansas in December 1945. He went back to fixing tractors. He never spoke publicly about his contribution to the Merlin program. When neighbors asked about his war service, he would shrug and say he was just a mechanic. He received a letter of commendation from the Army Air Forces. He kept it in a drawer with his discharge papers. His children didn't discover it until after his death in 1987. The warm-up protocol he developed became standard procedure for all piston aircraft engines. It's still used today. No textbook credits him. Colonel Marcus Henderson, the officer who nearly ended the Merlin program, served with distinction through the rest of the war. He commanded a bomber group during the Pacific Campaign. He never publicly acknowledged that he had been wrong about the bearing failures. In 1952, Henderson wrote a memoir about his wartime service. Jesse Vincent's name appeared once in a footnote. But di san thuk su qua Vincent, kung nam o huan chung, he saklik su. It lived in the techniques his engineers had pioneered. The manufacturing methods Packard developed for the Merlin transformed modern industry. Statistical process control, precision casting, dedicated tooling systems, real-time quality verification. These weren't just wartime expedients. They were revolutionary approaches to manufacturing that changed how the world builds complex machinery. When General Electric developed America's first jet engines after the war, they used techniques pioneered at Packard. When Pratt & Whitney built the engines that powered the first commercial jet airliners, their production methods descended directly from Vincent's assembly lines. The bearing metallurgy that Packard's engineers developed, the silver-lead alloy with indium plating, became standard in high-performance engines worldwide. Racing engines, aircraft engines, industrial turbines. All of them use bearing materials whose lineage traces back to a Detroit factory in 1941. The thread compatibility approach that Vincent insisted upon influenced the development of international standardization. The ISO metric thread system, which unified global manufacturing standards in the 1960s, was partially inspired by the lessons of World War II. Engineers remembered the chaos of incompatible fasteners and vowed never to repeat it. By some estimates, more than 200 million engines built since 1945 have used manufacturing techniques that Packard pioneered. Not directly copied, but descended through chains of industrial inheritance that trace back to East Grand Boulevard. Several Packard Merlins still fly today. The Canadian Warplane Heritage Museum operates a Lancaster bomber with 4 original Packard engines. At Reno Air Races, unlimited-class P-51’s with heavily modified Packard Merlins produce over 800 horsepower, nearly 3 times the original specification. Those engines are more than 80 years old. They still run. They still perform. They still demonstrate what American engineering achieved when necessity demanded the impossible. But the greatest legacy isn't technical, it's philosophical. Vincent proved something that bureaucracies still struggle to accept. Expertise can come from unexpected places. Innovation doesn't respect credentials. Sometimes the best solution to a precision engineering problem comes from a man who builds luxury cars. Sometimes the answer to a metallurgical crisis comes from a tractor mechanic. The military establishment of 1944 nearly killed the Merlin program because the solution came from the wrong people. Henderson dismissed Vincent's insights because he built automobiles, not aircraft. Henderson dismissed Kowalski's observations because he was an enlisted man from Kansas. They were both wrong. History is filled with similar patterns. The machine gun was dismissed by cavalry officers who couldn't imagine warfare without horses. Radar was nearly abandoned because the scientists developing it weren't military men. Penicillin was ignored for years because Alexander Fleming was a researcher, not a physician. Revolutionary ideas almost always come from people working at the boundaries of established fields. They see connections that specialists miss. They ask questions that experts consider too obvious to ask. Vincent asked why British tolerances had to be preserved exactly when tighter American tolerances would work better. Kowalski asked why engines that worked fine in California failed in England. Simple questions. Revolutionary answers. The lesson applies beyond warfare. Every organization, every institution, every bureaucracy faces the same challenge. Good ideas don't arrive with credentials attached. Innovation doesn't submit proper paperwork. The next breakthrough might come from the least expected source. The question is whether we're wise enough to listen. And there's one final detail that almost nobody knows. In 2003, a researcher named Graham White was examining declassified British documents about wartime technology transfer. Deep in the archives, he found something extraordinary. A letter from Rolls-Royce to the British Air Ministry, dated September 1944. The letter acknowledged that Packard's manufacturing techniques had solved problems that Rolls-Royce had struggled with for years. It recommended that British factories adopt American methods for bearing production impeller balancing and quality control. But the critical passage came at the end. It must be admitted. The Rolls-Royce engineers wrote that the American approach has produced a superior engine by measures we would not have considered. Their tolerances are tighter. Their consistency is higher. Their production rate is greater. We have much to learn from this collaboration. Rolls-Royce. The company that had invented the Merlin, the engineers, who had initially doubted that Americans could match their craftsmanship, had formally admitted that the student had surpassed the teacher. The letter was classified for nearly 60 years. Vincent never saw it. He died believing that the British engineering establishment still viewed his work as a crude imitation of their art. He never knew that they considered it an improvement. There's a deeper irony here. The Merlin engine that Packard built was fundamentally a British design. Stanley Hooker's two-stage supercharger, Henry Royce's original V12 architecture, decades of British aeronautical research. But the manufacturing revolution that made it available in war-winning quantities was purely American. Henry Ford's assembly line philosophy. Frederick Taylor's scientific management. The Detroit tradition of mass production that had built the automobile industry. Neither nation could have done it alone. British innovation created the Merlin's revolutionary design. American manufacturing made it available in the quantities that war demanded. 55 523 engines, built in 48 months, more than all British factories combined. The alliance wasn't just military, it was industrial. It was philosophical. It was a fusion of two different approaches to engineering that produced something greater than either could achieve separately. That's the real lesson of the Packard Merlin story. Not that American production is better than British craftsmanship. Not that mass production is superior to precision engineering. But that combining different strengths, different perspectives, different philosophies can solve problems that neither approach could solve alone. Vincent, the automotive engineer, and Kowalski, the tractor mechanic. Rolls-Royce, the luxury brand, and Packard, the mass producer. British innovation and American scale. Each contributed something essential. Each was incomplete without the other. So here's where we end. From a luxury car company with no aircraft experience to 55 523 engines that won the air war over Europe. From a tractor mechanic's observation about cold weather to a protocol that saved hundreds of pilots' lives. From an engineering challenge that Rolls-Royce called impossible to a manufacturing revolution that changed how the world builds complex machinery. Jesse Vincent never sought fame. Bill Kowalski never wanted recognition. Packard Motor Car Company no longer exists. But every time a modern jet engine is assembled using statistical process control, every time a high-performance bearing is manufactured with silver-lead alloy, every time engineers from different countries collaborate on a project too big for any single nation, the legacy of that Detroit factory lives on. 50,000 American airmen came home because of what happened on East Grand Boulevard. That's worth remembering. The next time someone tells you that an idea is impossible, that the solution can't come from outsiders, that the old ways are the only ways, remember this story. Remember the car company engineer who built better aircraft engines than the specialists. Remember the Kansas mechanic who solved what PhD metallurgists couldn't. Remember that the greatest victories often come not from doing what everyone expects, but from having the courage to try what everyone calls impossible. If you know similar stories of forgotten innovation, of unlikely heroes who changed history, share them in the comments. History is full of Jesse Vincents and Bill Kowalskis. Most of them have been forgotten. They deserve to be remembered. This was just one story. There are hundreds more. Subscribe to discover them. And remember the words that might have been carved above the door of every military bureaucracy in history if anyone had the courage to put them there. The expert who says it can't be done should not interrupt the amateur who is doing it.